Hello all. Today we'll be continuing our examination of data analysis in Excel. Specifically, in this tutorial, we'll look at how to conduct t-tests as well as how to interpret the results. Now, as you'll all remember from your readings as well as from your videos, t-tests are used when comparing two groups. Specifically, when we want to see if two groups differ significantly on a same variable. For example, we're going to look at our television, physicians, and life expectancy data set that we used for descriptive statistics. So take a minute and call that up. Okay, now that you have that up, let's say we're interested in looking or comparing between female and male life expectancy. In other words, whether there's a significant difference between the two, whether females on average live longer or shorter than males. So let's talk about how we'd actually conduct this analysis and what the findings mean. As you'll remember, to conduct analysis in Excel, we're always going to start by going to the Data tab. So I'll click off and then click back on. Here's our Data tab. And we'll go over to Data Analysis. Now, when conducting a t-test, you'll see that Excel will give you three options. A t-test paired two samples for means, a t-test two sample assuring equal variance, and a t-test two sample assuming unequal variances. Generally, we're going to choose between t-test, use one of the two t-test two samples. Paired two samples for means generally are also referred to as before and after designs. That's used more often when we're actually conducting experiments and we want to see how a single individual has changed over time. In other words, we're comparing someone against themselves later in time. The other two, when we look at two sample t-tests, mean just that. We have two samples. So in this example, we have a sample of females and a sample of males that we'll be comparing, both coming from the same country. So that's why we're going to use the two sample. Now, deciding between whether to use assuming equal variances and assuming unequal variances can always be a bit tricky. Some statistical packages will provide you with the information of whether or not the variances are equal, and when they mean equal, they really just mean close enough. Unfortunately, Excel doesn't do that, so you kind of have to go with your gut. Generally, you could run descriptive statistics and see if the variances are all that different, though in reality, both these tests will also provide you with the variances. So we're going to run both just so I can show you how they look, slight differences. In general, though, you're going to go with a t-test sample, two sample, assuming equal variances. The variances have to be widely different for it to have a major impact. But you don't have to take my word for it. I'll actually show you this in this tutorial. So let's go ahead and select two sample, assuming equal variances. Okay. So click OK. It's going to bring you to another window, or I'm sorry, another pull-up menu. It says t-test, two sample, assuming equal variances. So now it's going to ask you for the variable 1 range and the variable 2 range. So in this, you're actually going to, for variable 1, select the first variable that we're interested in. In this case, we're looking at female life expectancy. So let's go ahead and select that entire column. So I started at the label, female life expectancy, and I'll scroll all the way down to the end, down to Zaire. We'll do the same thing with variable 2 for males. So again, we start at the top with male life expectancy, scroll all the way down to Zaire. And this is what's going to be used to calculate between the two. So let's do that again. Sorry, that didn't work that time. Let's see. Let's try it one more time. There we go. Okay. So, hypothesize mean difference. You can leave that blank. Labels we want to include, right? Because we have our labels up here, so we want to make sure it's not going to include it or count it as numbers. The alpha level, this is when we have level of significance, so you can choose between 0.05 or 0.01. Since we're just kind of curious, we're looking at life expectancy, we're not going to use this to come up with a new policy or even to publish. Let's just stick with the 0.05 level. All right, that's all you need. Now let's hit OK. When you hit OK, you'll see that a new sheet will be created. So let's click back for a second. This is our original sheet with all our data. And right next to the left, here's our sheet with our output. So let's take a look. I'm going to move this column over a little bit so we can see all of the labels. So it gives us a few pieces of information. First, here is our row with our means. So you can see just by examining the means of the two groups that women look like, on average, they live about 5 years longer than males. So that's a pretty big difference, but just looking at that alone, there's not enough information for us to determine whether that's a significant difference. So let's look at a few more rows. So variances. This is the variance, as I mentioned. Notice that in females, the variance is higher than males, meaning that in women, the life expectancy varies more around that mean. In other words, while women live longer on average, there's more variability. More women are living longer, and more women are living shorter lives than males. But this doesn't tell us if that difference is super big or too big, so we have to use the unequal variances. But right now, we'll just keep going, assuming they're equal. Observations, that's just how many observations. We had 40, right, because we had 40 countries, so we had 40 observations for females, 40 for males. Pooled variance, that's just used in the calculations. You don't need to worry about that. Hypothesized mean difference similarly. Degrees of freedom, also not important in this case. And here is the key. These 5 columns. These 5 rows. This is where you will determine whether or not the difference is significant. So, the t-statistics, that's what's actually calculated. That's through all the mathematics, through all the calculations you'll see in your book. This is what we actually come up with. But we're actually comparing this t-statistic to another t-statistic, what are known as a t-critical statistic, on rows 12 and 14. So, in general, what we say is that if the t-statistic is larger than the critical t-statistic, we have a significant difference. So here's our t-statistic, which is 2.72, as compared to the t-critical, which is 1.66. It'll also tell you in 11 and 13 whether or not what the actual probability is. So, it seems a bit backwards, but this is how we interpret it. Since the probability that we selected is 0.05, if the probability that is displayed here is less than 0.05, then we know there's a significant difference. So for instance, when we look at this first piece statistic, we can see that it is less than 0.05, much less in fact. Therefore, we can conclude that the difference between male and female's life expectancy is statistically significant, that it exists in the population. So one last thing, you may also be asking yourself, why are there 2 piece statistics? Well, notice that one says for one tail, and the other one says for 2 tail. Now, as you might remember from your reading as well as the video, one tail test versus 2 tail test determines whether or not in your hypothesis you thought there was going to be a difference in a specific direction. So in a one tail test, you're saying that you predict there is a difference going a specific way. So for instance, your research hypothesis in this case might be that the mean life expectancy of women is longer than the mean life expectancy of men. So if you're doing that, if you're making a hypothesis in a specific direction, you'll use a one-tailed test. Conversely, if you're not sure, if you think there's a difference between the two groups, but you're not quite sure which way it could go. In other words, you're just going to say, there's a difference between male and female life expectancies, but I'm not sure which one's going to be higher. I think there is a difference, but I'm not sure which one's higher. That's when you use a two-tailed test. So generally, we tend to just use two-tailed tests because unless there's clear prior research that tells us of a direction, we'd like to be better safe than sorry. So in general, we're going to use a two-tailed test. But you can see here it doesn't really make a difference. Whether it's a two-tailed test or a one-tailed test, the difference is large enough. Okay. Let's go back to our data set for a second and run one more t-test assuming unequal variance. So we'll go back to our data tab, all the way over to our data analysis menu. That'll open up. And you can see this is what we just used, is 2 samples assuming equal variance. Let's click on assuming unequal variance and hit OK. Same as before, we're going to select female life expectancy for the variable 1 range. So we'll go all the way down, select all the way down to Zaire. Sorry, it didn't take. You can see I just selected the 1 column, the 1 cell. So let's do that one more time. Hopefully this will work this time. And sure enough, there we go. Let's also do it for men, which you can see is actually already selected, but We'll reselect just to be sure. There we go. Labels will keep. We'll keep the alpha at 0.05, and all we have to do is hit OK. So let's take a look at the output, and we'll compare it to the other output for equal variances. So, first thing to point out, sheet 4, this is assuming unequal variances, as it says up here. Sheet 3 is equal variances. I'm going to switch back and forth between these quite a bit, just to show you that in this case the variances aren't large enough to justify using unequal variances. So as you notice, the means are the same between two groups as between both ways to calculate the t-test. You also see that the variances don't change, correct? See, the variances are the same for both, which makes sense. Observation's the same. Now, notice in sheet 3 there's a pooled variance, and in sheet 4 there is no pooled variance. So when you're assuming unequal variances, there's a separate calculation, a separate formula for calculating the t-test that doesn't take into account variances, because what happens is, because of the way the formula is calculated, or the way the t-test is calculated using the formula, it relies on variances. So if the variances between the two groups are very, very large, that can really have an impact. That can be the overriding impact on whether or not you're going to find a significant difference, not the differences between the means. So unequal variances uses a slightly different formula. But you'll notice, if we go down to the t-statistic, notice that they're identical. So we come out to the same. What changes are the t-critical scores. So if we look at the t-critical score for one-tailed t-test, assuming unequal variance, you'll see it's 1.665. If we go over here, we'll see that it's 1.664. So you can see there is a slight difference, but negligible. So you can see, while the variances appear to be relatively different, the difference isn't large enough for us to justify using unequal variance. This is just to illustrate, excuse me, this is just to illustrate why 99% of the time you're just going to go ahead and run with a t-test, two-sample, assuming equal variances. I wouldn't spend any time at all at this level worrying about equal versus unequal variances. For a pilot test, it makes sense to use the 0.05 level of significance, and if you're running a t-test, to do a two-sample, assuming equal variances. Okay. So that is all for this tutorial. If you have any questions, let me know.